session 17 of ITCS 2022. Roughly the topic of this session is algorithmic graph theory, and you can see all of the full talks on YouTube. In this session, what we're going to do is, as is tradition for ITCS, I'll give a couple minutes of introduction to the papers, and then each of the 5 papers will have about 10 minutes to present. So the 5 papers in this session are the following. So we have a unifying framework for characterizing and computing width measures, fixed parameter sensitivity oracles, FPT algorithms for finding Near-Cliques and C-closed graphs, vertex fault-tolerant emulators, and correlation detection in trees for planted graph alignment. So all of these papers have some unifying theme to them, and that unifying theme is unification. So that is to say, all of these papers take several different ideas and unify them. And I would argue that this is an important thing to be doing, especially today in theoretical computer science, as the field has gotten larger and has had more and more sub areas and a wider reach. It becomes increasingly important to take different concepts and develop theories that unify them. So I'll describe briefly how each of these 5 papers fits into this theme. Okay, so the first paper is called A Unifying Framework for Characterizing and Computing Width Measures. It actually has the word unifying in its title. And what this paper does is okay, the slides seem to be there, like, okay, there we go. What this paper does is that they study a graph measure that captures several different already well-studied graph measures, such as tree width, clique width, and mim width. The next paper is called Fixed Parameter Sensitivity Oracles. And what this paper does is they combine the ideas of sensitivity oracles with fixed parameter tractability. So traditionally, sensitivity oracles have been studied mostly for distances, whereas this paper says, let's apply the idea of sensitivity oracles to some classic fixed parameter tractable problems, such as k-path and k-vertex cover. The next paper, FPT algorithms for finding Near-Cliques in C-closed graphs. This paper actually presents a unification of theory and practice, in the sense that they develop an algorithm and prove theoretical guarantees on it. And this algorithm actually behaves similarly to algorithms that have already been used in practice in the past. And in particular, these algorithms are for finding communities in social networks. The next paper is vertex fault-tolerant emulators. And this paper combines the ideas of fault tolerance and emulators. And emulators are a graph structure that are similar to another graph structure called spanners. And the punchline of this paper is that in the standard setting where you don't have fault tolerance, it turns out that spanners and emulators have similar bounds or the same bounds. Whereas if you go into the fault tolerant setting, emulators actually perform better than spanners. The final paper in this session is correlation detection in trees for planted graph alignment. And for this paper, what they do is they define a new statistical problem called correlation detection in trees. And then they take this new problem and draw connections from it to a previously studied problem called partial recovery for graph alignment. This is the end of the overview. So with that, I will stop sharing and welcome the first speaker. You can go ahead and share your screen.
Oh.
So the first speaker.
Okay, one moment. I have to. Okay.
The first speaker will be Lars Jaffke, and the presentation is about a unifying framework for characterizing and computing width measures.
Yeah, thank you for the very nice introduction. So what I'm going to talk about in this talk is width measures of graphs. And before I start and get into the details, I just want to give you a general picture of what this usually looks like. So we have some graph G, and we want to decompose it in some algorithmically useful way. So one way of doing that, for example, as it's done in tree width, is that we take subsets of the vertices of the graph and we arrange them in a tree-like structure, right? And then you get a picture sort of like this. And then you put some technical conditions on top that will make this decomposition useful in algorithms, okay? All right, and then the width of this decomposition is a numerical value that tells you something about the complexity of the decomposition. Right, so as I said, in this example, one way of measuring the width would be to just look at the largest vertex subset that you have in this tree structure. Okay, and this is actually more or less how the tree width of a graph is defined. Then the width of a graph is just a minimum width over all its decompositions. Okay, and why are these things useful in algorithms? Well, very often you can just move along the tree and do some kind of dynamic programming procedure. And very often this gives you algorithms that are polynomial time if the width is constant. Okay, so there are, of course, several width measures that have been defined, and the way you define these width measures can be very different from one to the next. So we have these two examples. So on the left, we have something that roughly corresponds to tree width, and here on the right, I show how we define the clique width very roughly. So in clique width, what you do is you have, again, a certain tree structure, but this time the tree represents like a series of operations of how to construct your graph. And in particular, you do this with labeled graphs. So for example, here you take a disjoint union of two graphs, and then there are some other operators that, for example, tell you to connect every vertex labeled 1 with every vertex labeled 2, and so on and so forth. And now the width in this case is the number of labels that appear in this tree or in this construction sequence. And it doesn't matter if you understand the details of this now or not. The point is that you can see that these things are very, very different from each other. Yeah. But at the same time, we call both of these things width. All right. Now, there are, like I said, there are many width measures that have been defined. And so these are some of them. And one thing that you can do is you can look at these width measures and ask yourself, okay, how powerful are they? In the sense that you want to look at the families of graphs that they are bounded on. And then you can derive a hierarchy like this. So in this picture, the width measures that are higher up are strictly more powerful than the ones that are below. Right? And if two width measures are in the same box, then they are bounded on the same kind of graphs. All right. So, okay, so what we did in this work is we had a look at this sort of picture. We take a step back and we want to know, is there something that these width measures have in common, right? Can we search for some unifying theories why we call some graph invariants width and others we don't? All right, and if you want to do such a thing, there are two things that you have to do. One is you have to unify the way you decompose the graph. And the other one is that you have to unify the way in which you measure the width of this decomposition. Okay. So, all right. So the way we did this is the following. So the type of decomposition that we look at basically corresponds to a recursive decomposition of the vertex set of the graph. So you can think of this as kind of a divide and conquer scheme that you want to run on your graph. So you take your graph G, you split it into two smaller parts, And again, you split these into two smaller parts and so on. And okay, and then, so what would be the width of such a decomposition? So think like you decompose your graph into these small pieces, and then you want to solve your favorite problem. Once you arrive at the small graphs, of course, it's trivial to solve the problem, but then you have to go back up and you have to combine solutions for the smaller graphs in order to obtain solutions for the bigger graph. And at this stage, it's of course important what is the structure of the cuts that appear along this decomposition, right? So if you have a very simply structured cut, then combining two solutions, combining a solution from one side and from the other is probably quite simple. While if you have a very complicated structure here in this cut, then it might be a bit more difficult. And this is why we say, okay, the width of such a decomposition is basically the complexity of the cuts that appear in this process. But again, there are many ways of measuring the complexity of these cuts. And in fact, there are many width measures that have been defined using this type of decomposition. So one example is you just take the maximum matching size that appears across the cut. And another example would be to take the GF2 rank over the binary adjacency matrix of this bipartite graph. So again, you see that there are many different ways of measuring the complexity. And what we want, again, is to unify the way that we measure the complexity here. And the way we do it is as follows. So we basically consider a family of bipartite graphs F, and then the corresponding F branch width counts in every cut what is the largest size of any graph that appears as an induced subgraph across the cut that is contained in your family F. Okay, so now you can, now you have this width parameter, and for every new graph family F, you get some new width measure, but you can see that they're all defined in the same way. All right, so I'm cheating here a little bit. We are not really caring about the size of the graph, but rather the intersection of the vertex set of a graph with one side of the cut. All right. Therefore, we also require some symmetry constraints. So we don't really want to have a different complexity if we look at the cut from left to right or from right to left. Therefore, we only allow bipartite graphs that have equally sized sides. Okay. Second of all, it's sort of unnatural to skip width values, right? If you have a measure that says you have some graph of width 3, some of width 5, but none of width 4, that doesn't really make sense. And therefore, we require that this family has to require a property we called partner hereditary, which is the following. So you look at these bipartite graphs and you partner up every vertex on the left with one vertex on the right. And then you require that if you look at any subset of the partners, then this again induces a graph in your family F. So for example, here, family F1 does not have this property, because if we take, for example, everybody except the first pair of partners, then we have an edgeless graph, and this is not a graph that is in this family F1. On the other hand, F2 does have this property because every subset of the partners just gives you a smaller matching, and this is the family of all matchings, and therefore it has this property. You have to hurry up a little bit. So what does this capture? So in fact, for all of these width measures that are marked green, we can find some family F that gives us something that is at least asymptotically equivalent to this width measure. All right, but this may not be so surprising because you can just have there are many choices that you can make. You can have so it's not surprising that there's some family of graphs that actually matches one of these width measures. But in fact, we show that you can restrict yourself further. So we say that a family is size identifiable if for all n, there's precisely one graph of order 2n in your family. And then we show that if you have some family f and you basically throw out all your graphs except the ones that are from a size identifiable family, then what you get is still equivalent to your original width measure. And the nice thing is that there are only 6 bipartite graph families that have these properties, and they look like this. So it's the edgeless graphs, matchings, chain graphs, and the bipartite complements. To summarize, there are many width measures out there. We want to find a unifying framework that characterizes many of them at once. And so there are 2 things we had to do. We unified the decomposition method. Here we chose this method of branch decomposition. Then we unified the way we compute the cut function. And we saw that this already captures many of these width measures. And interestingly, there are only 6 graph families that we have to use for this family F to give different width measures. All right, and we also showed that if your graph has low tree width plus max degree, tree depth, or feedback edge set number, then we can approximate any of these width measures efficiently. Okay, that's it. Thanks for your attention.
Okay, are there any questions for Lars? In the meantime, the next speaker, Martin, you can start sitting up.
Currently, the sharing is tech.
Okay, I'll move right along, but if anyone has any lingering questions, we can also have time for to ask questions to all of the panelists at the very end. Okay, great. So our next speaker is Martin Schernick, and the topic of the presentation is fixed parameter sensitivity oracles.
As Nicole already stated very nicely in the beginning of the session, it's essentially about proposing a new research direction by combining ideas from 2 areas that were previously disjoint. The first one is that of sensitivity oracles, where the idea is to maintain the graph property under edge failures. So in this example, we have certain pairs of vertices and the shortest paths in between them. And it might be that if some edge fails in that graph, that the distance increases, and we want to prepare for that. The specific thing about sensitivity is that these failures come in batches, but we know their maximum number in advance. This is the sensitivity F. We know that we only have to prepare for F failures at most. This is also the main difference to dynamic graphs, where these edge modifications come one by one, but are potentially unbounded in number. And to get an oracle, we want to pre-process that graph once into a small structure that we can then query when needed. So specify some failing edges and get the graph property back. And this is mostly researched for polynomial time computable properties. For example, all pairs shortest path, the conductivity of that graph. But some very interesting graph properties are not polynomial time computable, as we know. But some of them are at least fixed parameter tractable, which is the other area. That means the input graphs come augmented with some integer parameter. We have seen in the last talk, for example, it could be the width. In my examples, it will be the solution size. But the common thing is that we restrict our attention to graphs with parameter k. Then this can be computed in time. Do you see my mouse? Anyway, then this can be computed in some function of k times some fixed polynomial. So the textbook example is that if we only care about a vertex cover of size k, We can compute one if one exists in time 2 to the k times k times n. And it does not matter whether we fix k to 2. This is then a linear time algorithm, or for 42, this is still a linear time algorithm. And we observed that many FPT algorithms have, in some sense, innate fault tolerance. So if you think of the standard branching algorithm for vertex cover, in the same time bound, you can not only compute one solution, but all of them. For decision problems, this is not necessary, but this sort of redundancy can be made into fault tolerance. And to make this explicit, we propose fixed parameter sensitivity oracles, which are oracles with the sensitivity f for some FPT property. And to make clear what we really want is we fix the same parameter k for all queries. So the only thing that changes over queries is the set of failing edges. And what we strive for is some preprocessing time of some function of f and k times some fixed polynomial. So if you so will, something FPT in the parameter f plus k. So this sensitivity fits nicely in this parameterized setting also in this sense that you can just define it as another parameter in that sense. What we do not want is just something in k, because we can achieve this by essentially cycling through all failure set and computing from scratch. So this does not give us anything. And as query time, we want something that is significantly faster than computing from scratch, which of course depends then on what is known about the FPT property in question. There are some works for FPT on dynamic graphs, but none of these works take into account this fixed sensitivity f, so the maximum number of failures we have to prepare for. And we think this is an omission, a gap that needs to be closed, because it really lends itself essentially as another parameter. And what is also interesting for ITCS, there was some work 2 years ago where they started with a classical fault-tolerant problem, something about fault-tolerant spanners we hear later, on some special graph class. And then they took the insights they gained there back to the classical FPT world, so essentially the other way around 2 years back. And as an example problem for this highlight talk, I have vertex cover. So this is the current fastest algorithm to compute a k vertex cover in this time. So this is the bar we have to beat for the query time, if you so will. And the first thing we showed is that some form of co-normalization, specifically for this vertex cover problem, also holds in the fault tolerance sense, and that you can compute an equivalent graph whose size only depends on k and f in polynomial time, which is already pretty nice, because then your query time for all what you do later on, and also the space of your data structure, only depend on f and k, no longer on the input graph size. But still, what we inherit from sensitivity oracles is that you have to make careful trade-offs between the space you allow and the preprocessing time and the query time, which now all depend on f and k and how these parameters relate to each other. This is a pretty common observation for data structures, that there's not one single data structure that is best for all parameters. So here I confine myself to some f that is smaller than k, and still we'll have our hands full balancing here, space, preprocessing time, and query time. In our first solution, I already hinted at for vertex cover, we just take the standard branching and edge, add this edge fails option, and we get from this something in space 3 to the f plus k, which is essentially computable in time proportional to its space, but has a query time that depends only on f. So this is something you want to do if you only want to prepare or need to prepare for 1 or 2 failures, but want to know the information about large vertex covers. So if your k is super large, but your f is moderate, you might want to go in this direction, but still you might take issue with an exponential dependency on f. So we try to bring that down to something polynomial. Here I use the assumption that f is smaller than k, so there's something hidden in f. as well. But usually you pay for improvements on one side at the other. In this case, we get this k square in the exponent, which for large k might be much larger than already this 3 to the f plus k. So usually if you try to bring one of these down, something else increases. And if you want to bring, for example, this exponential space down to something polynomial in the parameters, we can just reuse what Elman, Mich, and Wasilewska-Williams did for dynamic graphs and get something in space k square. So even independent of the input size, so something you really want to do, for example, on small edge devices. But what you pay for this is super huge query time. It's almost what you would pay for computing a vertex cover from scratch. You get rid of the input size, but still it's a pretty huge query time. And this is the common theme that you have to balance these kind of things. To get to the open problems, nice thing about new research direction is that essentially everything is open. The most pressing things is to advance the fixed parameter sensitivity oracles to more problems. So we have vertex cover and k-path, as Nicole mentioned, but it would be great to have more of them. And we have to reduce the dependency on f and k. They are not optimized yet. We cannot hope for fully polynomial for FPT, but I think there's room for improvement, for example, to this 2 to the k square. And something I didn't have time to mention in the highlights, we also found some applications of parameterization in the classical fault-tolerant world, in the sense that sometimes if you relax the objective in some parameterized sense, you can sidestep known lower bounds, which is, I think, pretty cool. And with this, thanks a lot.
Are there any questions for Martin? Okay, Shweta, you can start setting up. Again, we'll have more time for questions for all of the panelists at the end. So the next talk will be by Shweta Jain on FPT algorithms for finding near-cliques in C-closed graphs.
Hi, everyone. My name is Shweta Jain. I'm a postdoc at the University of Utah. This is joint work with Balram Behra, Edin Hussein, who's here in the audience today, Timrof Garden, and my PhD advisor, Seshadri Komandor. So the inspiration for this work actually comes from real-world graphs. Subgraph counting is one of the most important problems that is looked at on such real-world graphs. And we look at subgraphs like cliques, near-cliques, where by near-cliques we mean cliques that are missing a small subgraph. And the reason these are important is because they're used in many applications, including community detection, edge prediction, spam detection, clustering, and many, many more. So many of these problems, these subgraph counting problems, are actually NP-hard. And yet, something interesting has happened in the last few years. Many extremely simple backtracking algorithms have proven to work very well in practice. And there have been a number of works that have appeared in the last few years, each of those progressively trying to get better and better runtime in practice. And to give you a sense of how well these perform, they're able to count cliques and near-cliques in graphs with millions of vertices and edges in minutes. So this is a plot from one of our recent papers. On the x-axis, I have 4 big real-world graphs. The sizes of these graphs are in the table on the right. As we can see, they easily run into millions of vertices and edges. And so the y-axis has time in seconds on log scale. So ignore the red lines for now. The lightest blue line corresponds to the time taken by this algorithm to count all cliques in these graphs. And the slightly darker ones, they correspond to the time taken by the algorithm when it was also trying to count the per vertex and per edge clique counts, which are harder problems than getting just the global counts. And as we can see, in 3 out of 4 cases, the algorithm actually terminated in minutes. In the case of ORCUT, it took about a couple of hours. And this was on a commodity machine. And this algorithm is sequential, although it can be parallelized, but this version was sequential. And so the bottom line is that these algorithms work very, very well in practice. So clearly, the structure of the graph is helping the algorithm perform well. It is not worst case. And so from the point of view of beyond worst case analysis, this raises an important question, which is what structure is leading to this behavior? So in order to address this, a graph class called C-close graph was recently proposed. This was proposed in 2018 by Jacob Fox, Timur Karden, Seshadri Kumantur, Fan Wei, and Nicole Wein. And the idea here was to capture this notion of triadic closure, which is a property that a lot of real-world graphs show. And essentially, what it says is that a friend of a friend is likely to be a friend. So a lot of these 2 paths tend to be cliques, tend to be triangles. So the formal definition of this graph class is a graph has C closure if every pair of vertices that have C or more common neighbors are themselves connected, which means that if you have these 2 vertices, U and V, which have C or more neighbors, then there has to be an edge between U and V. And if G is C closed, then it is also C plus 1 closed, C plus 2 closed, and so on. So we pick the lowest value of C. So here are just some examples. For C equals 1, it's a disjoint union of cliques. You can have C equals 2, C equals 3, and so on. So in the same paper, the authors showed that maximal clique enumeration can be done in FPT time. And this is a surprising result, considering that in general graphs, even approximating the max clique is cannot be done in FPT time. So following this, there were a series of works counting different kinds of patterns. One notable work is that of Kwon from 2020, computing dense and sparse subgraphs. This paper also counted k-plexes, which is also one of the Near-Cliques that we looked at. So this was part of this was concurrent work at that time. And then there have been a number of works that have tried to that have showed that a lot of these NP-hard problems are actually fixed parameter tractable. So what we do in this work is we show that enumerating several kinds of Near-Cliques can be done in FPT time, and we give algorithms for that. So the Near-Cliques that we look at are D+1 plexes. So these Near-Cliques that we looked at, in some sense, they are dense graphs. So it might be easier to think of them in terms of the sparse version of these graphs in the complement graph. So a D+1 plex is basically the complement of a bounded degree graph. And so we also looked at complement graphs of bounded degeneracy graphs, complement graphs of bounded tree-width graphs. Our proofs, they come in 2 different flavors. So the first one is simple. It uses a very simple backtracking approach. And the second one uses the 3-step approach that was used by the original authors. And both of these have their advantages. So the first one, being closer to reality, or the algorithms that are used in practice, it gives a better sense of why these algorithms are working fast. And so in some sense, it bridges that gap between theory and practice. And the second approach, it has the advantage that in certain cases where we don't yet have backtracking algorithms, this approach can still give us FPT bounds. And so in some cases, in fact, this approach can end up giving us tighter bounds as well. So in the process of proving these results, we also proved that we also gave a Moon-Moser type bound for the number of 2 plexes in general graphs, and this bound is tight. This is the only other known result of this kind other than the Moon-Moser bound for number of maximal cliques. And we also showed that some kind of subgraphs cannot be enumerated in FET time. So not all kinds of such Near-Cliques can be enumerated in FET time. We also gave a very simple backtracking based algorithm for counting, for enumerating maximal cliques. And we will very briefly look at this algorithm. The algorithm from Fox et al. Was not backtracking based. And so this led to newer understanding of why clique counting is fast in practice. Okay, so I'm going to very quickly describe a very generic algorithm. And many of the clique counting algorithms that are used in practice are sort of specialized versions of this algorithm. So what does this algorithm do? Given a graph, it orders the vertices of the graph and orients the edges from lower to higher vertices. And in this way, it converts it into a DAG. And now one can show that if you want to get all cliques in the original graph, essentially that boils down to getting the cliques in the out neighborhoods of each of these vertices. So what does the algorithm do? It looks at these out neighborhoods, and we are now interested in finding the cliques in these out neighborhoods. So it's the same problem we started with. So what does the algorithm do? Same problem we started with, just on a smaller instance. So the algorithm recurses. And so for every vertex in these out neighborhoods, we spawn a branch, calculate the new out neighborhoods. So in this case, 1 and 5 is in the common out neighborhood of 6 and 8 is in the common out neighborhood of both 1 and 5, and so on. And so basically at every recursive call, we have some subgraph that we are interested in getting the cliques in. And this process continues until there are no more subgraphs left. And one can show that basically every path here from a root to any node in this forest, this gives us a unique clique from the original graph. All the blue nodes at level 1 correspond to cliques of size 1, and at level 2 correspond to cliques of size 2, and so on. And basically the size of this enumeration forest is equal to the number of cliques in the graph. So what happens in the case of C-closed graphs? So think of, consider a missing edge UV in the original graph. We're going to define two kinds of nodes. So if the subgraph that we're looking at, if that subgraph is a clique, then we know that we don't need to explore that branch further. We can just take that clique, combine it with the vertices on the path, and get a bigger clique, and then we can check for maximality. But so there are leaves are cliques, and then the internal nodes of this tree, they have to have some missing edge. So consider a missing edge from the original graph, say UV. The question is, how many nodes or how many subgraphs can this missing edge appear in? So remember that everything that is on the path to that node has to be a neighbor of UV. And since we are in the C-closed setup where UV is constrained to have no more than C common neighbors, that means that the number of such unique paths that can lead us to a node that contains the edge, missing edge UV, can be at most 2 to the C. And so since we have at most n square missing edges, that means that the number of internal nodes here would be at most n squared times 2 to the C. And since every internal node can have at most n children, that gives us that the size of the tree can be at most n cubed times 2 to the C. And if you're a little more careful, you can show that it is actually n squared times 2 to the C. Okay, so that was just to give a taste of what kind of things we can do in the C-closed setup. We show results for D+1 plexes. These are complement graphs of bounded degree graphs. And so, for example, a1 plex is basically a clique. So the trivial bound is 2 to the n times n squared. And only very recently, someone showed that this can actually be done in gamma d to the n times n squared, where gamma d depends on d, and the value of gamma d is less than 2. And so this was shown very recently. And what we show is that in this C-closed setup, you can actually find all maximal d+1 plexes in time n to the 2d times 2 to the c. And in the process of showing this, we also showed that the Moon-Moser type theorem, which says that the number of maximal duplexes in general graphs can be at most 10 to the power n over 5, and this is tight. And we also show that enumerating co-d-degenerate graphs. So a graph is d-degenerate if every induced subgraph has at least one vertex with degree at most d. And so a graph is co-d-degenerate if its complement is d-degenerate. And what we show is that maximal co-d-degenerate graphs can also be enumerated in time n to the 2d plus 4 times 4c. Similarly, we show a result for bounded co-tree width. We showed that they can be listed in time n to the t plus 4 times 4c, 4 to c, where the co-tree width is at most t. Okay, so to conclude, we showed that a number of Near-Cliques can be enumerated in FET time in this C-closed setup. And we also give a tight bound for the number of duplexes in general graphs. But the most important message from this work, which is what one of our reviewers pointed out, is that there are natural backtracking-based algorithms in practice for finding large cliques in practical graphs. And the newly proposed C-closed analysis framework for the first time explains why. And thus, further study of this C-closed framework is one of the most promising directions for theoreticians to contribute to this practically important algorithmic setting. Thank you.
Okay, in the interest of time, we need to move straight on to the next speaker. So Yasmin, you can set up.
Sure, can you stop sharing, please? Thank you. All right, so yeah, this talk is on vertex fault-tolerant emulators, and it's a joint work with Greg Budwin and Mike Dinitz. Okay, so let me start by defining spanners. Given a graph G, we say that a subgraph H is a T-spanner of G if for all nodes UV, the distance between U and V in H is at most T times the distance between U and V in G. So for example, here you see this graph G, which is a dense graph, and then you see a sparse subgraph that preserves the distances up to a factor 3 for all pairs. Okay, so what is an emulator? An emulator is similar to a spanner, but it does not have to be a subgraph. So still for all nodes, we want to preserve the distances up to a factor T. And the difference here is that we're allowed to add edges. So for example, you see a graph G here, and you see a tree emulator, and you see that we could add some new edges here. Okay, so the main question in the context of spanners and emulators is that we are given a parameter T, which is the stretch or the approximation factor, and our goal is to see how many edges we need to get a T-spanner or a T-emulator for a graph with n nodes. And we know the answer to this question. We know that for any k, at least 2, any graph has a 2k minus 1 spanner with roughly n to the 1 plus 1 or k edges. And we also know that assuming Ehrlich-Gersh conjecture is true, this is optimal. Also, as Nicole pointed out in the intro, we know that spanners and emulators are in a sense equivalent in a sense that even though emulators have this additional flexibility where we can add edges, this does not seem to give us a better stretch and size trade-off. But the interesting thing that we show in this talk is that when we think about fault-tolerant settings, this equivalence no longer holds. So we can indeed get fault-tolerant emulators that can be sparser than spanners with the same stretch. And before I get into that, let me tell you what I mean by fault tolerance. So spanners and emulators are generally used for distributed computing and networks. And Their application is usually in routing and communication. We want a sparse subgraph that we can use for routing. But of course, in networks, nodes can fail. So for example, here, let's say we have this red spanner with these red edges, and then one node fails. So this spanner is no longer useful for us. So in a lot of practical settings, it makes sense to think about spanners and emulators that still hold the stretch guarantee after a certain number of faults. In particular, we say that a graph or a subgraph is F vertex fault tolerant if its property that it is still a T emulator or a T spanner, even after a set of size F of nodes fail. So again, in non-faulty settings, we know how to get optimal size and stretch trade-offs, as I mentioned. And here our goal is to see, with respect to this parameter F, which is the possible number of faults, what is the size guarantee that we can get? And note that this definition is easy to understand when we talk about spanners. Spanners are just subgraphs. But when we think about vertex fault tolerant emulators, we have to answer another question, and that is, how are we going to set weights for edges that were not in the original graph? Basically what we need to hold for this fault tolerant emulator to be correct is that for all nodes U and V, we need to ensure that the distance in H minus F is at most T times the distance in G minus F between the endpoints, and it's also at least the distance between U and V and G minus F. So what are our options? The first option that comes to mind is what we would do when we construct emulators classically. So we set the edge weights for any node that is that we add to be the distance between the endpoints. The problem with this definition is that as soon as there's any fault set that increases the distance between U and V, this is going to cause a problem for correctness. We're basically going to get an underestimate if we set the weights this way. So the alternative is to do the following. So let's say UV is an emulator edge that was not in G, and we define the edge weight to be the shortest path distance after faults. So weight of this edge is D sub G minus F of UV. And in a sense, we're saying that we are allowing ourselves to update the weights after faults. And if you think about it, this is really the only natural option that allows us to even construct fault-tolerant emulators. But other than this theoretical motivation, I want to argue that this also makes sense in practical applications. So one practical thing that's very close to emulators is an overlay network. An overlay network is basically a set of logical links where routing in a network takes place along the shortest path on these logical links. And basically overlay networks are just emulators. So let me show you an example. So for example, let's say we have this logical link between E and G, and what happens is that routing protocols basically forward a packet along the shortest path between the two endpoints of this edge. So in a sense, application-specific routing protocols already do something that is very similar to this automatic weight updating. They basically send the packets along the shortest path after faults. So it makes sense to do things this way even in practice. And the quality of the routing would depend on the quality of our emulator, or the stretch of the emulator. Okay, so let me get into our results. As I promised, we showed that we can construct emulators that outperform spanners with the same stretch for a given fault set F. Fault set size F. So in particular, we showed that we can get emulators that are sparser by at least a factor of roughly square root F. But in case of odd K, we can even go further and show a lower bound that basically says that our bounds are optimal with respect to this number of faults F. So there are two immediate open questions. The first one is, what is the deal with this difference between even and odd K? The second question is, our bounds have some exponential dependence on K, and it would be good to eliminate this dependence, even though our main goal was optimizing based on F. Finally, we also have some results on additive emulators. And here we even get a much stronger improvement when we think about fault-tolerant emulators. And in particular, we get an exponential improvement. In particular, there's a lower bound that says if we want to construct plus C additive spanners for any constant C and fault sets of size at least log n, we basically need n square edges. So we just can't sparsify. But we show that we can get optimal simple algorithms for F vertex fault tolerant emulator for +2 and +4 emulators. And these are the bounds. So with that, let me conclude. So a few open questions. As I mentioned, we would like to close the gap for even K and remove the dependence on K in our bounds. Also, we want to see what happens if we have edge failures instead of vertex failures. And it's also good to see if we can get any algorithms for other related objects, such as distance circles. With that, I finished. Thank you, and please watch the full video for more details.
Okay, let's have the last speaker set up. Okay, so we now have our last talk is by Luca Ganasali, and the title is Correlation Detection in Trees for Planted Graph Alignment.
Okay, hi everyone. All right, hi everyone. My name is Luca, and I'll be talking about correlation detection in trees for planted graph alignment. So since I have only 10 minutes, I will only give a glimpse of the work we did. So please do not hesitate to watch the full video or to come to me for further details. I'll be very happy to discuss. So this is a joint work with Laurent Massoulier and Marc Lelarge. So first of all, what is graph alignment? So, well, the graph alignment problem is a very simple question, which is what is the best way to match the nodes of two graphs, right? Imagine that you are given two graphs, G and H, and you simply looking for a natural way to match the nodes of the first one with the nodes of the second one. So this is a bit unclear, so we have to formalize it mathematically. So if we have the same number of nodes in the graph, we want to find a bijection that minimizes the following quantity here. So you can easily recognize that minimizing this quantity is like looking for quasi-isomorphism, right, between our graphs. In the case where G and H are isomorphic, well, this is just the isomorphism problem. So here, graph alignment can be viewed as a noisy version, if you like, of the graph isomorphism problem. So minimizing this quantity is actually can actually be rephrased as an optimization problem over the set of permutations, which is, as you probably know, an instance of the quadratic assignment problem, which is known to be NP hard in the worst case. So what people usually do with these problems is that they study not necessarily the worst case version, but the mean case version. So this is what we are going to do now. So the correct problem now we are looking at is the planted graph alignment. So what is planted graph alignment? The idea is to study the problem in a mean case setting where the graphs are now random. So they are now drawn under a random model. And we actually plant a solution in our data. So we know more or less what is the underlying vertex correspondence pi star. And we will try to recover it. Of course, just upon the observation of the graph, right? We of course we hide this this solution, but this is a way to judge the performance of our algorithms, right? We know what is the underlying ground truth, if you like. So the model is very simple. It is the standard heterotraining model for graphs. So we simply need here to introduce some correlation between the graphs. So we draw two graphs, say a blue one and a red one, and edge per edge independently, we sample the colors of the edge. So the edge can be two colored, meaning that it will appear in both graphs with probability lambda s over n. With probability lambda 1 minus s over n, it is monochromatic, so red or blue only. And with the remaining probability, there is simply a non-edge, right? And as I said, we also need to plant a solution. So we simply relabel, say that the second graph uniformly at random. And this will be pi star, will be the ground truth in our model. Right, so lambda here and s are two parameters. Lambda is the mean degree of both graphs that have same marginal distribution. And s is this correlation parameter. You can see that if s is 1, for instance, the graph will be isomorphic. But in general, s is between 0 and 1. So the goal now is to estimate, we are in an inference, Bayesian inference problem. We want to estimate the latent vertex correspondence pi star. And the regime we are looking at is what we call the sparse regime, since in terms of signal, the number of edges is of order n. So we have an average degree which is constant, and the correlation is also constant, not scaling with n. A first remark in this setting is that we cannot hope for exact recovery. We cannot hope to recover every single vertex in the correspondence. This is just because in this regime, there are too many isolated nodes in the graph. So if I give you some isolated nodes, of course, there is no way to match them better than just random guess. So we are aiming at an estimator who overlaps pi star over a non-vanishing fraction of the nodes. So the contribution in this paper is to design a local algorithm, which actually simply looks at neighborhoods in the graphs. And we'll see that this will bring us to another problem, the tree detection, the tree correlation detection problem. So why is that so? Well, we are given two nodes in G and H, and the question we are asking is, okay, is node I mapped to node U under the underlying ground truth pi star? Well, a simple answer, just exploring the local neighborhoods, is to look at these neighborhoods, which are in this regime rooted trees, and given a certain depth, we are left with two trees, and what we want to be able to tell is whether these trees are correlated or not. So this is an hypothesis testing problem, and to be more precise, what are the hypotheses? So here, if we're in the situation where I and U are matched, the two neighborhoods will look like in this regime Galton-Watson trees up to depth D, but they will have a common intersection, right? They will be correlated in terms of edge presence. Otherwise, as a first approximation, if we take two nodes far apart, well, the two neighborhoods will be simply independent trees, right? So this is the typical hypothesis testing. We have the same marginals, but under the null model, they are just independent. Under the model 1, they are correlated. So the goal is to test P1 versus P0. To do so, we simply compute the likelihood ratio, so the ratio of probabilities. And looking at this quantity actually can bring interesting ideas because this quantity enjoys a quite simple recursive computation in terms of depth, right? So looking at this likelihood ratio at depth D is simply a function of likelihood ratios of subtrees at depth D-1, right? So this brings a polynomial time algorithm when D scales at most like log n, and n is the number of vertices in the graph. So this will simply be our algorithm acting like scores, if you like, who will tell you whether you and I are matched or not. So just a summary of the results in the paper, please have a look at the whole video to learn a bit more. So we are looking for one-sided tests. I told you that we were going to do partial recovery. The goal is a bit more, in fact. We are asking to output only pairs for which we're quite certain, right? So we don't want any mismatch. This is quite logical in terms of application, because if I tell you I have a permutation, but only half of the nodes are correctly matched, you will tell me, okay, where are they? So here we just want to output maybe half of the nodes, but half pairs will be correct ones. So the results in the paper, so we give theoretical sufficient necessary conditions for there to be a one-sided test in a tree problem. So this can also be translated into some conditions on the parameters lambda and s. The algorithm on trees that I described, simply looking at this likelihood ratio, easily extend to the graph setting, where we end up with a polynomial time message passing algorithm for this graph alignment task. And these conditions for the tree problem, of course, give also conditions on the parameters for the feasibility, the polytime feasibility, if we like, of the partial graph alignment problem, which improves the phase diagram. So the phase diagram now is as follows. We already knew about these red and blue phases. So we know that this red phase here is the impossible phase. We don't have signal is not powerful enough. And then over lambda s equals 4, we know that theoretically there is an exponential time algorithm that succeeds. But what this contributions tend to do is to characterize. So this is only what is proven for now. Of course, we conjecture that these phases are much wider, but we have this easy phase. So easy phase here means polytime feasible with our local algorithm for graph alignment. And we also exhibit a phase where the parameters would enable information theoretic feasibility, but our algorithm, however, this local point of view fails. And this may be a clue and a first clue about the existence of a hard phase for this problem. So this is a first glimpse of what may be the wide hard phase for this graph alignment problem. All right, so I'm done with this presentation. Thank you very much. And please don't hesitate to come to me for further info.
Thank you so much to all of the speakers and your wonderful talks this session. So even though we're over time, I want to open it up to anyone who's still here if you have any questions for any of the speakers.
Actually, I have a question to these vertex fault-tolerant emulators, especially the last part about sidestepping this lower bound. This is also something we observed, and it's interestingly from the same 2017 source, but we relaxed the objective in the sense that you have to preserve certain distances, and we now only preserve those that get perturbed by this parameter k. And this way we sidestep one of these bounds. And can you give some intuition on how what you do to improve on the lower bounds?
You said you've sidestepped over a lower bound for two different objects, or?
Yeah, for this fault-tolerant spanner from a single source, where you want to compute the spanner where you preserve all fault-tolerant distances from a fixed source to any target. And there's this n square minus 1 divided by f of plus 1 lower bound. So essentially quadratic, which is pretty similar to what you showed. But if you now only preserve distances that get an additive increase by at most k from any f failures, so you no longer preserve all distances. This is essentially the idea. You relax the objective, and then you can sidestep this lower bound. My question would be, what were you doing in a nutshell to get around
right.
this?
So the thing about these emulators, the way we've defined them, is that it basically allows us this weight updating is kind of giving us some more power. And it's kind of, I mean, I have explained the algorithm in the full talk, but it, in a sense, it lets us connect some paths with these edges that we can add with emulators that would otherwise not be possible with spanners. So in case of fault-tolerant spanners, we just have to maintain a subgraph. But here, like when we add the spanner edges, along with those spanner edges, we end up adding some additional emulator edges. We weren't allowed to do this with spanners, and this basically lets us add fewer edges in total. And why does it go below the spanner bound? It's just how the analysis work. Like there's an averaging argument on how things work and how we can count these paths and these edges, and basically we get something that is sparser. But yeah, I don't know a very short answer.
It was already very insightful. Thanks a lot. That definitely answered my question.
Okay, yeah, let me know if you have questions later.
Okay, thank you to all the speakers again, and bye everyone, and have a good rest of ITCS.
Thanks, bye.
Thanks, Nicole, bye.